Hello and welcome to this clip introducing alcohols. We'll take you through the structure and naming and the classification of them, and we'll look at their simple reactions such as combustion. We'll cover the basic physical properties of alcohols and we'll do a worked examination question at the end. We'll cover oxidation of alcohols and reactions of alcohols in a separate clip. So the structure of an alcohol has three main parts to it. You have a main body of the organic molecule. We sometimes write this as R for simplification if we're just talking about the behaviour of the alcohol itself. We have a carbon atom that's attached to the main body, or part of the main body of the organic molecule. And attached to that carbon atom is a polar hydroxyl group. So the hydroxyl group is OH. You can see the oxygen has two lone pairs on it. There's a delta negative oxygen and a delta positive hydrogen. So it's interesting to note how the carbon-oxygen-hydrogen bond angle has been included of 104.5. So that slight bend in the molecule reflects that. Now obviously the carbon atom will clearly have other things bonded to it. So for the time being what I'm going to do is just put the two bonds in. But not actually populate them in anything, because what is actually bonded to that carbon as well as the OH has quite a lot of bearing on the classification of the alcohol, which we'll talk about next. So when you're naming alcohols, what you do is you count the longest carbon chain, you identify it, and you number the carbons from the end closest to the OH group. You include the number of the carbon the OH group is attached to, and end the name in ol. So this would give us pentan 3-ol on the left, and 2-methyl propan 1-ol on the right. So on the left-hand side, it doesn't really matter for pentan 3-ol because the hydroxyl group is equidistant, that is 3 carbons in from either end. It doesn't matter which end you count from. We happen to count left to right this time, but we could count from right to left. With 2-methyl propan 1-ol, the carbon atoms are counted at the end closest to where the hydroxyl group is attached, so in this case right to left, as you can see. So carbon 1 is where the hydroxyl group is attached, and we count along from there. So when we classify alcohols, we take two things into account. Firstly, how many hydrogen atoms are attached to the carbon atom the hydroxyl group is bonded to, and then how many alkyl groups are also attached to the carbon atom the hydroxyl group is bonded to. So if we identify the carbon atoms we're talking about, and we also name the alcohols, now what we can do is explain the classification of each one. So looking at each alcohol in turn, I'll deal with methanol in a second. With ethanol, you have 2 hydrogens attached, and you have 1 alkyl group, so it's called a primary alcohol. With propan 2-ol, you have 1 hydrogen attached, and you have 2 alkyls, so this is called a secondary alcohol. With 2-methyl propan 2-ol, you just have 3 alkyl groups, so this is called tertiary alcohol. Methanol just has 3 hydrogens. It's unique amongst the alcohols, and it doesn't really fit the classifying criteria. So what we do is we classify it automatically as a primary alcohol. The reason for this is it follows the same chemistry as primary alcohols. Now the chemical behaviour of the different types of alcohols is outside the remit of this video. There's another clip in the series that talks about that. I need to apologise slightly for the seagulls in the background. I think they're trying to contribute to the video clip. But just to reiterate what I said there, primary alcohol chemical behaviour is shared with methanol, so methanol would actually classify as a primary alcohol, even though it doesn't share the same structural criteria that we talked about this time. So when we look at cyclic alcohols, we're assuming that these are alcohols that have the OH directly bonded to one of the carbons in the ring. So in the case of the example shown, the OH group is assigned to carbon number 1. The next substituent along can either be at substituent number 3 or at substituent number 4. So the correct version is the version I've drawn in purple, where it's at substituent number 3, because the second substituent then gets the lowest possible number, as per the ruling. So
the alcohols in this particular screen would be named 3-methylethyl cyclopentanol, cyclopentanol, and cycloheptan 1,2-diol. And the diol part comes from the fact that there are two OH groups. If you had 3 hydroxyl groups, you would have triol. So alcohol molecules hydrogen bond easily to each other, so as a result their boiling points are higher than similar sized organic molecules from other homologous series. So this means that they easily dissolve in water as well. So, for example, alcohols and water can mix very, very easily. This is obviously put to use in alcoholic drinks, where drinks can be watered down, for example. So what's happening is the hydrogen bonding taking place between the ethanol and the alcoholic drink, and the water that's added to it means that the two liquids can mix easily. When we're doing equations for the combustion of alcohols, it's exactly the same as doing the equation for the combustion of a hydrocarbon or any other organic molecule. The only thing you've got to take account of is the oxygen that's already present in the hydroxyl group as part of the alcohol molecule. So let's do an example. If we were to take propanol, it's not included in the examples on the screen. So you'd start off by writing your propanol and adding it or reacting it with oxygen. You know that the carbons will become carbon dioxide, you know that the hydrogens will become water, so it's easy to write CO2 and H2O on the right. These will be standard products. So this particular version of propanol is propan-1-ol, the primary version, because it's got the OH group, the hydroxyl group, coming off one end, and therefore it has one alkyl group, the propyl group, and 2 hydrogens attached to the carbon that the OH is bonded to. So the first thing to do is to deal with the carbons. There are 3 of them, so that means you'd get 3 carbon dioxides. You have 8 hydrogens, so you'd have 4 H2Os. So you have 6 oxygens contained in the carbon dioxide. You have 4 oxygens contained in the water, which means you've got 10 oxygen atoms in the products. So therefore what you've got to do is you need to have 10 oxygen atoms in the reactants. So although it would be tempting at first to put 5 in front of the oxygen, the problem with that is you've got this oxygen in the OH group to contend with. So therefore what you've got to do is take that oxygen in the OH group into account. And you do that by taking one of the oxygen atoms from the OH and including it in the total. So 4.5 O2 is actually 9 oxygens. So the extra oxygen you need comes from there. So now we've actually managed to achieve our 10 oxygens. So it's something to keep an eye out for if you're trying to do a combustion equation balancing it for an alcohol. Always include the OH in your calculation. So you could sum it up this way. First thing you do is you balance the carbons. Make sure each carbon in the alcohol becomes a carbon dioxide. Next up is the hydrogens, but don't forget that water, one molecule of water contains 2 hydrogen atoms. And finally balance your oxygen, but don't forget to include any oxygen atoms that are in the alcohol molecule itself. And don't forget to factor in how many OH groups you've got if you're dealing with a diol or a triol. So it's very easy to measure the enthalpy of combustion of an alcohol. You can use calorimetry using this apparatus. Remember, the alcohol will be in the spirit burner at the bottom. So you weigh the spirit burner and then you set it up using the apparatus shown and light it. And to try and keep it as efficient as possible, we have a draft shield and we try and set it up so the spirit burner's flame is as close to the water as possible. So you measure the temperature rise, you extinguish the flame and reweigh the spirit burner. You apply Q equals mc delta T, which you'll have looked at obviously when you're doing your work on enthalpy. And to work out the enthalpy of combustion, it's the Q value in kilojoules divided by the moles of alcohol burnt, and the moles of alcohol burnt can be obtained by mass over mR. In a nutshell, that's how you do it. Obviously you'll have opportunities to do this in your practical sessions, but it's a technique and a calculation that you'll need to be quite familiar with, not only in terms of the ways in which the technique is kept as efficient as possible to avoid heat loss, but also what to do with the data that you've measured and how to actually calculate Q equals mc delta T and also the enthalpy of combustion itself. So although the details of this are covered in a separate video clip, it's worth spending a minute or so going over it, again, just so you're familiar with what to do. So let's have a look at an exam question. You're given some data, and it says the alcohols are an example of an homologous series. So an homologous series is going to be a family or series of organic compounds with the same functional group, very similar properties, and each successive member increasing by CH2. So what you've got to do is look at this and think to yourself, what's the general formula of a member of the alcohol homologous series? And you write it like that because you have to actually include OH in your general formula, because the OH signifies the hydroxyl group being present. So it asks next for the molecular formula of the alcohol that has 13 carbon atoms per molecule. So I've taken N, turned it into 13, and just applied that. So I didn't write in OH this time because the molecular formula just lists the number of each type of atom. You don't put in the OH if they actually ask you the molecular formula. So a functional group is a group of atoms or part of a molecule that gives a compound its chemistry, or its characteristic set of chemical reactions that set it apart from other types of functional groups. So let's bring the page down a bit. And it says at room temperature and pressure the first four members of the alcohol homologous series are liquids, whereas the first four members of the alkanes homologous series are gases. So explain this difference, and it's 3 marks they're offering. So alkanes have London forces of their own intermolecular force, so you've got to make a similar comment about alcohols. So once you've made a statement about alkanes and alcohols, you have to try and make a comparison between them, and that's how you pick up your 3 marks. You make a separate statement about alkanes and alcohols, and then you compare the two by making a comparative statement explaining difference in boiling points, like you've been asked to do. So it says methyl propan 1-ol and butan 1-ol are structural isomers. It says methyl propan 1-ol has a lower boiling point than butan 1-ol, and it asks you to suggest why that might be. What I reckon the best thing to do at this point is to draw them both out so you can try and work out what's going on. So in the interest of saving space, you can put skeletal formulae, and you can clearly see that one of them is branched and the other one is not. So if you think back to your work on the basics of organic chemistry and the differences in boiling points between non-branched and branched compounds have lower boiling points than non-branched compounds. So the first thing we say is that methyl propan 1-ol has weaker London forces than butanol, and you've got to qualify it by saying that the reason is that methyl propan 1-ol is branched, so it has less surface area for London forces to act on. The next one is about complete and incomplete combustion of methanol. So remembering that complete combustion produces CO2 as a product, and incomplete combustion produces carbon monoxide or carbon as a product. So I start by putting my methanol, my oxygen, my carbon dioxide and my water out on an equation. I haven't balanced it yet, so what I've got to do now is start with the carbons like we talked about earlier in the clip. There's 1 carbon in methanol, so you can keep it as 1 carbon dioxide. There are 4 hydrogens in methanol, so you will need 2 waters. Now to take into account the oxygen in methanol, you now have 4 oxygens on the right hand side, so therefore to have 4 oxygens on the left hand side, including the oxygen in methanol, you need to make this 1.5. So now we can do the incomplete combustion, and again what we can do is put in the same unbalanced equation, but because the only thing that's changing is the number of oxygens in my products, the hydrogens don't change, so I'm keeping it as 2H2O. And double checking everything, it's already balanced. I don't need to change anything to the O2 on the left hand side. So then it says suggest what conditions might lead to the incomplete combustion of methanol. And like any hydrocarbon combustion, alcohols being organic will burn in the same way in an insufficient supply of oxygen. So it will be a lack of oxygen in the air. Okay, so let's move the page down a little bit. So it says, in addition to its use as a fuel, methanol can be used as a solvent and as a petrol additive to improve combustion. Then it asks you to state another large-scale use of methanol. The easiest thing to do here is to refer to its use as a chemical starting material. The word we use is feedstock. And it's important to point out that it's used for making other organic compounds. So by the end of the A-level course, you'll have come across some of the types of organic compounds that we can use alcohols to make. Now this next bit is about the oxidation of alcohols. So if you're watching this video as preparation for your alcohols teaching for the first time, this bit won't be quite so relevant. If you're watching it as a review of your alcohols work, you'll obviously have been taught about the oxidation reactions of alcohols. So I'm going to put a little bit of a warning, a caveat, on the side of the screen. So I'm going to go through it anyway, but if you don't need this right now, because you're just watching this as a preparation for your first teaching, you can fast forward it slightly to the next part of the question. So now we're going to do a little bit of a review, and we're assuming that we're heating under reflux. And if you've done your work on oxidation of alcohols, you'll know that by oxidizing a primary alcohol like butan-1-ol under reflux, then you'll get a carboxylic acid. So one mark is forgetting the fact that you've got butanoic acid, your CH3CH2CH2COOH, and the other mark is for getting it balanced, including the water and also the two oxygens in square brackets. So let's now move on to the next page. So I'm going to whiz through this one fairly quickly, so I've put the answers in already. It says write the name and draw the structure of the structural isomer of C4H10O that is a tertiary alcohol. So next to where I've put tertiary alcohol, I've highlighted it at least, you can see that I've written the main sort of basic structure of a tertiary alcohol. So I drew the structure first, which gave me a carbon with the OH attached and 3 CH3 groups attached directly to that carbon. Then I drew the name in because by drawing the structure first, you can then work out the name. And again, the final bit, it says it's technically not within the scope of this particular clip. For the same reason that that part of the previous screen also is technically not within the scope of this particular clip, but I'm doing it anyway, just in case you're having a look at this as a review after you've had your teaching on oxidation of alcohols. So if it's oxidized to form butanone, that's a ketone, so the alcohol must have been secondary in its structure. So I started off by drawing my 4-carbon chain with the hydroxyl group in a secondary position. Then I could add the hydrogens in to make up my structure. So now let's go and have a quick look at the mark scheme. So you might notice that in the mark scheme they're talking about van der Waals forces. This is a pre-2015 specification paper. So the mark scheme will talk about van der Waals forces instead of London forces. You must use London forces in all your answers involving temporary induced dipole-dipole interactions. It's really important. So let's quickly whiz through. We got our 2 marks here, and we'd already worked out our general formula and deduced the molecular formula. So here we're saying London forces instead, just like I've said. But apart from that, we did get the mark. So 2 different statements, and then we compared them using the hydrogen bonds being stronger. So we made reference to methyl propan-1-ol having weaker London forces, and then we talked about it having less surface contact or more branching. What I did was actually put both of those in there, So that mark would come from either of the two sentences on either side of it. What's important to say here is if you say just more surface area, without making reference to the idea of it being surface area that the London forces can act on, then that's not enough. So that's why I said in my answer, surface area over which London forces can act. So looking at the next scheme, we got our correct equations. We talked about insufficient supply of oxygen, and we've got our, in our oxidation part that we were doing as a review, we got our carboxylic acid and we've got the equation. So the equation is 2 marks out of 2. Just getting the carboxylic acid would be only 1 mark, like so. It's worth pointing out as well that if you put equations that don't have full structural formula in them, you only get 1 mark. If you put equations that don't show full oxidation, as suggested by reflux, you only get 1 mark. If you put just molecular formula, you don't get marks for it. So always put the structural formulae. And the reason for this is the examiner needs to know that you know exactly what functional groups are involved in the reaction. Molecular formula don't tell you this, so don't be lazy and put molecular formula. Sorry to be frank with you about that, but it's really important that you don't fall into that habit. In the next part, we got 2-methyl propan 2-ol, and we got butan 2-ol as our answer. So where it says don't allow a horizontal bond, then HO, the reason for that is that the bond actually is to the oxygen in the hydroxyl group, not to the hydrogen in the hydroxyl group. So what I'm trying to say, I guess, here is it's that way round. So sometimes people get a little bit sloppy and make that kind of mistake as well. And you can see that highlighted down here as well. So very, very important to get that bit right. Okay, so thanks for your time on this. Hopefully it's been a fairly useful introduction to certain aspects of the alcohols, and if you're reviewing alcohols, it's included a little bit of oxidation reactions as well, although they're covered in a slightly different clip. So if you have any queries, please bring them to your class, please have a chat to your teacher about it, or maybe come in and see one of us during a subject extension at college. But in the meantime, like I say, thanks for your time and appreciate it, and see you soon.